Okay. So let me start again. We defined open cover first. What was an open cover? Open cover is a collection of open sets whose union covers the subset E, right? We call a collection like this an open cover for a subset. And we define that subset an compact subset provided that it every open cover has a finite subcover. And then we showed that using the definition any finite subset is compact, and we showed that a sequence like this together with its limit point is a compact subset. And then we showed that okay, so we proved the same thing for any no, I left it as an exercise, the same thing with the sequence and its limit. And then we showed that this unbounded set R is not compact, and we showed that this subset which is not closed is not also compact. And then as a complementary fact, we proved that a compact set of xt is necessarily closed and bounded. And we ended this by the following. We showed okay, as a corollary of that, we proved that if we have a compact metric space, then it must be complete. And finally, we showed that every sequence in a compact metric space has a convergent subsequence. Okay. Last time I forgot to state and prove the following, so let me start with that proposition. Maybe before I start, do you have any question from last time? Okay, so this is kind of the converse of the above proposition. A closed subset E of a compact metric space is compact. So if you start with a compact subset, then it is closed. But when it comes to be a subset of a compact metric space, then the subset will be closed if the subset is closed. Okay, so if E is a subset of a compact metric space, then E itself will be compact if and only if it is a closed subset. Okay, how can we prove this? Well, we will just apply the definition. Okay, sorry. So let OI be an open cover for E. So E is a subset of this OI's subset. I want to show that finitely many of these open sets covers E. Okay, you don't need all of them, only finitely many of them will be enough, but we don't know which finitely many of them. All right, how can we do this? Well, we know that E is closed and the metric space is compact. Okay, now let this metric space to be X metric space. Let me say X is okay. Then okay, since E is closed, uh, X minus E, let me call this set O, is open. Okay. Well, I have some open sets covering E, and the complement of E is also open. But then X, which is E union X minus E, okay, and E is a subset of these open sets, and X minus U is already an open set. So what I get is then this collection, these open sets together with O is an open cover for E. So that this collection together with O is an open cover for X. But we know that X is already compact. Since X is compact, finitely many of these open sets already cover X. X is inside finitely many of these open sets, this collection. So let's say I1, I2, let's say IK, and maybe I will need also this O. If I don't even need O, I may just write it here. Okay, for some I1 up to IK. Okay, in the index set, of course. But then you see, then uh, E is a subset of X, and E intersection O, which is O is X minus E, is empty. We have what? We have this. E is a subset of this I1, I2, and IK. So what I have obtained, I started with an open cover, right? Open cover, sorry, open cover for E, and I showed that E is a subset of finitely many of these for some indices. This means that E is compact, right? Hence, E is compact. This finishes the proof. Okay, any questions so far? Okay. All right. Okay. Uh, okay. Let me talk about now compactness and convergence of sequences. Uh, okay. We proved already about that compactness and convergence of sequences. We proved that in a compact metric space, any sequence has a convergent subsequence. We will show that the converse is also true, and actually that is equivalent being compact. But first, I need an another concept called pre-compact subset. Okay, first we have a definition. A subset E of X is called pre-compact. Pre-compact. If what happens? If for every epsilon positive there are uh, finitely many x1 up to xk in X so that E is a subset of the balls with center xi and radius epsilon. Okay, so this is like being compact, but it is slightly different, right? Here, you give me an epsilon, I need to find finitely many balls with radius epsilon that covers E. If I can do this for any epsilon you give me, then we call this set E pre-compact. As the name or pre-compact suggests, this is something weaker than compactness. And actually, we have the following. Okay. So we have as a proposition, a compact set is pre-compact, a subset of a pre-compact set is also pre-compact, and a pre-compact set is bounded. Okay. Let's see why this is true. Uh, well, assume E is a compact subset. I want to show that E is pre-compact. So for the first statement, uh, so uh, so we claim E is pre-compact. How can we prove this? Proof of the claim. Okay. Given what was the definition? Given epsilon, I should be able to cover E by finitely many open sets. All right. We can do this as follows. For any x in E, we have what? X is inside, of course, in the ball of radius x and center x and radius epsilon. Hence, we see this x, which is the union of one point sets, not x, I'm sorry, E, is contained in this collection, in the union of this collection, right? I just over about every point of E, I consider the ball with center x and radius epsilon. So this is E, and for each point, here, I consider this ball, okay, with radius epsilon. I do this for every point, okay. So they cover, of course, the whole set. So they form an open cover for E. In particular, this collection of balls is an open cover indexed by the elements, by the points of E, is an open cover for E, but E is compact. Since E is compact, this open cover must have a finite subcover. We see that E should be contained in finitely many of these open sets. So E should be contained in finitely many of these open sets means there is some open set from this collection. So with some center and radius epsilon, and then there's another one. How many of them? Only finitely many of them because E is compact. Okay, for some x1 xk in E, which is in X, of course. So we are done. Hence, E is closed. E is compact. Pre-compact. Sorry, pre-compact. Okay. So I had claimed that any compact set is pre-compact. I proved that in this claim. Another thing is that a pre-compact, if you have a pre-compact set, any subset of it's also pre-compact. That's easy. So I leave as an exercise to show that a subset of a pre-compact subset is also pre-compact. That's easy, right? I mean, trivial. Finally, let's just show that for the final statement, let E be a pre-compact subset of X. What we have to do, so we must show E is bounded. Okay. How can we do this? Well, you see, E is pre-compact, therefore E is contained inside finitely many balls of any radius. So let's, for example, epsilon to be 1. Since E is precompact, E is contained. There are points x1 up to xk in X with E is a subset of B x1 1, B x2 1, and so on, B xk 1. So I can cover E with balls of radius 1. Okay, so here is E, let's say. Okay, so this is E, and I can cover this by balls of radius 1. One ball, another ball, another ball, and so on. Okay, so this is, let's say, x1, and this is xi, and so on. Okay, well, if I have finitely many balls, then of course I can do the following. I can pick up a bigger ball, take any point here, okay, take any point, and measure the distance from this point to this centers, okay, centers. Let's say this is R1, this is Ri, and take the maximum. Okay, now take any point x0 in X and let Ri to be the distance from x0 to xi to the centers, I from 1 up to k. Let r to be the maximum of these distances, r1 up to rk. I can consider the maximum of these numbers because there are only finitely many of them. Okay, finitely many of them. If you want, let's add 1 to this. So uh, then clearly any ball with center xi and radius 1 will lie inside the ball with center 0 and radius r, right? Why is that? Because you see, if I choose any point here, the distance of this point to x0 will be, by the triangle inequality, less than this distance plus this distance. This distance is less than 1. This distance is less than Ri. So that this distance is less than 1 plus, because this 1 plus Ri, this distance here is always 1. So why this is true is easy to see this. Let y is in be xi1, then the distance between y to x0 is less than, by the triangle inequality, distance from y to xi plus the distance between xi to x0, but this is less than 1 and this is less than Ri. Maybe I don't even need this. Okay, so this distance is less than distance of x to xi is Ri, and Ri is less than r. Okay, Yeah, yeah, I should take this r plus 1 here. All right. So this distance is less than, strictly less than this, because this distance is strictly less than 1, and this distance is less than Ri. It might be equal to Ri. So uh, R is less than or equal to this number, but 1 is strictly less than this. Therefore, this is strictly less than 1 plus R. So that Y is in the ball with center x0 and radius 1 plus R. So what we see, any ball like this lies inside this gadget. So we have this inclusion for all I. Hence, E, which is contained in this union, finite many balls, but each one is contained in this ball. First one is contained in this ball, the second one is contained in this ball, and so on. Hence we are done, because E is contained in a ball of uh, finite radius in a single ball, so that E is bounded. So this finishes the proof of the proposition. Okay. Any compact subset is precompact. A precompact set is precompact. A precompact subset is precompact, and a precompact set is always bounded. Any questions so far? Okay. Well, finally we have the, this characterization theorem. Now we will state and prove the sequential characterization of compact subsets. And here is the theorem. The following conditions are equivalent on a compact on a compact on a metric space. Sorry, on a metric space. What are these? Let's say this is xt. Here is the conditions. Xt is compact. Every sequence in X has a convergent subsequence, and also the following: xt is complete and precompact. Okay. So we claim that these three properties are equivalent. X is compact, every sequence in X has a convergent subsequence, and xt is complete and precompact. We already proved the followings. Right? We have already proved that A implies B. We showed that if you have a compact metric space, then every sequence in X is has a convergent subsequence. Okay. We will prove first we will prove B implies C and C implies A. So the circle will be complete. Okay. Okay. First, let's prove that B implies C. Okay. So B means what? Every sequence is a convergent subsequence. So assume that every sequence in X as a convergent subsequence. We must prove what? We must prove that we must prove X is complete and pre-compact. So we must prove, must show X is complete and pre-compact. Well, let's see this. For the first part, X is complete. This is easy. Why is that? You see, to show that X is complete, I have to show that every Cauchy sequence is convergent. But by the assumption, we know that every sequence has a convergent subsequence. Therefore, that Cauchy sequence has a convergent subsequence. However, if you have a Cauchy sequence and if it has a convergent subsequence, then the whole sequence is convergent. Why is that? Because all the terms of the sequence are very close to each other. Therefore, if a subsequence converges somewhere, then the whole sequence must converge there. Okay, so take any subsequence xn, not subsequence. Take any Cauchy sequence xn in X. Okay, well, by the assumption, then by the assumption xn has a convergent subsequence, say x kn, okay, to, let's say, some x0, or let's say L. Okay, let's say x0. All right. Well, I want to show that this sequence converges to x 0, the whole sequence, but that's very easy. Why is that? So let epsilon be given. First of all, since the sequence is Cauchy, since xn is Cauchy, there is some uh, n 0 so that n greater than, or well, m and n larger than n 0 implies dxn xm is less than epsilon over 2. However, this sequence is converging to x0 also, since on the other hand, limit xkn is x0, and thus choosing n0 if uh, bigger if necessary, uh, we see that n greater than n0 implies the distance between xkn and x0 is less than epsilon over 2, right? Since the subsequence is convergent, there is some index such that after that index, the distance between the terms of the sequence and the limit point is less than epsilon over 2. And I just take the maximum of this n0 and this n0 and call it again n0, okay? That's why I just say that, I have already one n0 here. If necessary, just choose this n0, something bigger. This will still hold, and this will also hold, okay? This is the same thing as choosing n1 here, n2 here, and then letting n0 to be the maximum of these two. All right. But now then, so if n greater than n0, then the distance between x n and x0 will be what? Well, n greater than n0 implies this distance kn plus kn x0. Well, n greater than n0, we know that kn is an increasing sequence. This is a sequence, right, of positive integers, and kn is increasing. So both n and kn are larger than n0. But if both indices are larger than n0, then this distance is less than epsilon over 2. And this distance is certainly less than epsilon over 2. Therefore, this is less than epsilon over 2. So this is because, maybe I should write, because n greater than n0 implies kn is larger than n0, because this is an strictly increasing sequence of positive integers. Therefore, k1 is larger than 1, k2 is larger than 2, and kn is larger than n. In particular, kn is larger than kn0 if n is larger than n0. So what we have seen is then the following. I started with an epsilon, and I found some n0, so that if n larger than n0, then this distance is less than epsilon. This means that the sequence is convergent. Hence, limit xn is equal to x0. But you see, I started with an Cauchy sequence, okay, any Cauchy sequence, and I showed that it is convergent, so that, all right, so that xt is a complete metric space. So I proved half of the claim. We want to show that B implies C. C has two parts, complete and pre-compact. I proved that it is complete. Now let's see why it is pre-compact. That's also easy. So pre-compact. How can I do this? Well, if X wasn't pre-compact, then there is some epsilon so that finitely many balls with center finitely many balls in X with radius epsilon wouldn't cover X, because pre-compact means for any epsilon finitely many balls, I can choose finitely many balls with that radius which will cover X. So if it is not pre-compact, then there is some radius so that no finitely many balls of that radius, uh, no finitely many of balls of that radius will cover X. Now assume on the contrary that uh, XD is not pre-compact, but then there is some epsilon positive so that uh, uh, for any x1 up to xk in X is not contained in these balls. X1 radius epsilon, X2 with radius epsilon, and this. No matter how many of these balls you choose, there will be always some point in X which will lie outside, right? Pre-compact, it is not pre-compact means this. There is some ball, there is some radius epsilon, so that finitely many balls cannot cover X. But you see, this way I can form a sequence, right? I start with X1, and then I choose a point outside, uh, you know, so now we form the following sequence. Okay, start with any x1 in X. Since X is not contained in this ball, because finitely many balls of radius epsilon cannot cover X, there is some x2 in X minus b x1 epsilon. In particular, of course, in particular, the distance between x1 and x2 is, of course, greater than epsilon, because you see, x2 is not in this ball. Therefore, the distance between this point and the center of this ball is larger than or equal to epsilon. Okay, now I repeat the same argument. Now, since X is not a subset of this union, right? It is not contained in this. There is a third element. There is some x3 which is in X but not in this union. Okay. Hence, you see the distance between x3 to x1 is larger than or equal to epsilon, and the distance between x2 to x1 is larger than, no, x3, I'm sorry, x3 to x2 is larger than epsilon, because x3 is neither in this pole nor in this pole. Therefore, the distance from x3 to the centers of these balls is at least epsilon. Okay, you see, this is what I am doing. Here is my x. I consider a ball of radius epsilon first, and then I know that this ball cannot contain x, therefore I choose some x2, and then consider again the ball with radius epsilon. I know that these two balls cannot cover x, so there is some x3, and I just repeat this. So this way we form a sequence so that the distance between the terms of the sequence is at least epsilon. So by induction, we can form a sequence xn so that distance between any two terms of this sequence is greater than epsilon for any n different than m, right? I'll just repeat this process. But you see, you have a sequence and the terms of this sequence are at least epsilon apart. Epsilon is a fixed positive number. Therefore, the terms of this sequence never gets closer to each other. This means that this sequence cannot have an accumulation point. This sequence cannot have a convergent subsequence, right? Hence, this implies that xn has no convergent subsequence, right? Because if it has a convergent subsequence, then some of the terms of the sequence would be as small as we want. In particular, the terms of that subsequence would be less than the distance between the terms of that sequence would be less than epsilon after some point on. But you know, this sequence has no such terms, right? Any two terms are at least epsilon apart from each other. So that's a contradiction. Has no convergent subsequence, which contradicts to our assumption. Uh, so why we ended up with this contradiction? Because I assume on the contrary that X is not precompact. Hence, this assumption is false. Okay. Hence, Xt must be precompact. So this finishes the proof of B implies C. So what is left now? We will prove A, no, C implies A. So we assume that XT is a complete and pre-compact metric space. So we assume XT is complete and pre-compact. Sorry, pre-compact. And what we have to show is that part A, which means X is compact. And we must show XT is compact. Okay. And I'll do this in the second hour. So let's give a break now.